So for 0 to 60, the rate of change of the number of mosquitoes is this many mosquitoes per day. So just like in the video you just watched, we know that this is a rate. That's going to be important. There are 1,200 mosquitoes at time equals 0. So, at time equals 20, is the number of mosquitoes increasing or decreasing? Well, if your rate of change is positive, it's going to be increasing. Rate of change is negative, it's going to be decreasing. So we can just plug that in to our function, because that was our function's rate of change. Evaluate this, and we get negative 5.113. So we can tell that it's decreasing. And you'll find that a lot of questions are just really asking you, do you know how to use, like, what is the question asking? What part are they trying to get you to figure out? That's sort of a combination of ideas and techniques that we've used before. According to the model, how many mosquitoes will there be at time 60? Well, now we want to know mosquitoes, but the model is a rate of change. So this is where we use the accumulation of change. We know we started off with 1,200. Then, how much change between 0 and 60? Plug that into your calculator, and we get approximately 1,482 mosquitoes. And finally, to the nearest whole number, what is the maximum number of mosquitoes for 0 to 60? How do you recognize an extreme value theorem? It's going to ask you for a maximum or minimum and give you an interval. So what do we have to do? We have to find all the critical points and check our endpoints. And if we check all of those, they had a name where at the conference people were like, they had a name for these points. And I'd never heard people call it, but now I can't remember the name. It was like possible points. No, extrema are the maximum and min. But the points that you have to check, are the endpoints and the ones in the middle. And there's a really intuitive word that they use. Candidates, yeah. They use candidate points. That's exactly, did you see that on our video somewhere?
No, I was thinking of synonyms.
Yeah, that's me. It's something that like that. And I was like, what the heck are candidate points? Like, it seems weird to say. I don't think it's a necessary word, but you have to check all your candidates, all the ones that are possible. What are we going to do? We're going to find out where you have things equal to 0. It's equal to 0 at 0, at 6 pi, at 12 pi, and at 18 pi. So that's just our regular rate. Where's our rate equal to 0? Because that's your derivative already. And the exam and all the exam sessions I've gone to, they really recommend checking all 5 of those points. Figure out what 0 is. Well, you knew what 0 is because it was started. You already figured out what 60 is because you have it here. So you would just have to do 1,200 plus 0 to 6 pi to find that one. 1,200 plus 0 to 12 pi to find that one. 1,200 plus 0 to 18 pi to find the last one. That's what they'd recommend. Sometimes, right, what do we know with this being plus? It's like, ooh, can you see that based on these arrows, you do not have to check 12 pi? Because if you were curve sketching, it's increasing, then decreasing, then increasing, then decreasing. I'm absolutely certain that 12 pi is not going to be a maximum. It's a local minimum. Last time I checked, local minimums are also never local maximums. Unless you're the only person in your village. Then you might also be the tallest and the shortest person at the same time. But this is a continuous function. You wouldn't have to check that. But in most places that I've gone for exam checking, they say check all the points. Even though you know this one's a minimum, check them all. But here they're saying you technically would only have to check 6 pi and 18 pi, but I've seen on some exam marking that unless you write out a statement why you don't have to check the other ones, they sometimes take off a mark for that. So it's just easier to say, I'm using my extreme value theorem, I'm checking all the points. I know I don't have to check some of them, but that's okay. And then you're going to find out which one is the biggest, and it happens to be 1526. Okay, now we're going to have a little bit of fun. We're going to have a little bit of fun parabolas, and I'm going to start off with this parabola. I'm going to take a parabola that's open and down. I'm going to shift it over 2 units, so x plus 2, oh, I'm going to shift it to the, I'll shift it to the right. X minus 2 squared plus 4. Yeah, I like that. If I draw that parabola, would you agree that the vertex is at 2, 4? And it's opening down. Happens to work out nicely to have those as x-intercepts. That's that graph. So from our previous unit, if I'll call this, just instead of y, because I'm going to introduce another parabola, I'm going to call this one f of x. What am I finding if I do this? The integral from 1 to 3 of f of x dx. What does that mean, given the picture, and what does it represent? What is the integral from 1 to 3? This is f of x. This isn't the rate of change or anything like that, just f of x. What am I finding? Right, so here's 1, here's 3, and I find the area under that curve, which I love the crayons. Hardest part is the color choice. I'm going to go purple. Color that in. I'm mostly okay with the color, and I actually wanted to take a little bit more time, but I'm okay. I'm okay. I'm now going to draw another parabola. The parabola I'm going to draw this time, it's going to be in blue, g of x. I'm going to also move things over 2 to the right. But I'm only going to go plus 1. No, I'm going to go plus 2. I like that. And so my vertex for this one would be right there. Would you agree that that would be at 2, 2? And it would go over 1, up 1. And look like this. So if I asked you what this represented, that also would be the area under the curve from 1 to 3.
Students who are going on the field trip, please come to the front foyer.
Crayon-wise,
That's all WJHA
gonna
students
go
who are going on the field trip.
green.
Please come to the front
That would be
foyer right
this.
away.
Ooh,
Thank you.
I'm a little bit I don't know. The color mixing is a little bit dirty, but it's kind of brownish. Kind of feels like maybe something toxic. But we have that area under that. What we can now do, which I think you could see quite easily, is that I wanted to find this area here, could you see that you could just subtract the two? And integrals, I would just have to do the area from 1 to 3 of f of x dx minus the area from 1 to 3 of g of x dx. And if we think about some of our properties for integrals, we are actually allowed, if these bounds are the same and we're subtracting, this is the same as the integral from 1 to 3 of f of x minus g of x dx. Now I specifically nicely chose values where everything was above, because you always find the area below to the x-axis. But the beautiful thing about this is that I could, oh, there we go. Doesn't matter where that graph is, if I moved it, if I made part of it above and part of it below, when you were finding area under a curve, you'd have to then, think some of it's negative, some of it's positive. The beautiful thing about area between curves is that if you subtract one from the other, it automatically figures out above and below and doesn't worry about positives and negatives, and will calculate the perfect area between two curves every single time. So this is our first topic, area between two curves. And all it is the area under one curve, subtract the area under the other curve, we'll get the area between two curves. So in our last unit, I was amazed when we could find area under a curve when it was a weird shape. Now we're going to mix two weird shapes together and find the weird shape in between them and be able to find that area super easily. It is really cool. Oh, you might actually want to bring crayons to class so you can color into it's quite enjoyable. Everybody good? So in our first example here, if I take off my crayon, and I'm going to go orange, find the area in between these two curves. So it's going to be this part here I'm trying to find that area. Do you notice, though, that as far as subtracting the two areas, that this point and this point are going to be really important? You also have to sort of get a sense of which curve is going to be above and which curve is going to be below. However, if you screw up and do the below one minus the above one, you're still going to get the right answer, just negative. So if you ever do screw that up, you pretend like you knew it all the way along and just add absolute value bars along the way, perfectly fine. Okay? It's like, I meant to do that. I knew that. But if we can, we'd be like, oh, it makes sense that the parabola that's going down would be the one on the top, and the parabola that's going up would be the one on the bottom. If I color code things here, this is my red one, this is my blue one. How do I find out where those graphs are the same? Well, I'm solving a system of equations. And in fact, substitution works beautifully because they're already both equal to y, so we can just make the x's parts equal to each other and solve for x, where we get plus or minus 2. We can label those points. We don't really need the y values, but we could have them if we wanted. We have the point negative 2, 2, and 2, 10. So then if I want to find the area, I just have to do the integral from minus 2 to 2 of the blue graph minus the red graph. So again, if you screw up here and do the wrong order, you're going to get the same answer, but one of them is negative.
Can you go up a little bit?
Mm-hmm. Sorry. Is that enough?
Yeah.
Okay. That's a really weird area. We're going to find that. Like, something satisfying. Makes using like the old rectangle formula seem so boring. Like seems so elementary. You go, oh yeah, I can find a rectangle, no problem. But look at this shape. And the nice thing about subtracting them together, like you could find the areas under each separately. But then you're going to have to do more work. If you have them together, you can simplify. And the simplification will end up being an integral that's really easy to find. It's okay? Down to there? And each of these integrals are easy to find, so we can write out the proper notation for finding the definite integral, plug in our values. You can probably skip that part. You can write it if you want, but you can just write down the answer, because it's just mental math. So what's cool about this is even if some part is above and some part is below, and I like this example because if I think of the intersection points, and I think about, and I'm going to color code this separately, if I think about first figuring the area out beneath f of x, can you see, oh, crayon time, the green, this would be the area under f of x. And then we would subtract, and I'm going to take red out, the area under the red curve. And under the red curve, I would get this, but it would be negative, right? And I would also, now I'm going to take out my eraser, because I would also get this part again. Oh, that looks like it's struggling. It doesn't, oh, that's weird when I erase crayon. Wouldn't that cancel that out? And then, what happens when you subtract the red part? It becomes positive. And you would get exactly the red and the green put together as the area under the curve. What's beautiful in this example is it shows that it doesn't actually matter if some parts are above and some parts are below. When you find the intersection points and subtract them, you will get the positive correct area between the two curves, no matter if as in this situation, some's above and some is below. Because subtracting the negative part will make it positive when it's in there. And then just like I erased this little section that happened in both of them, in the one part, it counted that section as positive, but when you subtracted the other one, it just erased it out, and you get exactly the area of the curves between them. So we have to find our two intersection points, and again, color coding things. My parabola is in red, and my line is in blue there. I make them equal, and I solve, and I get 2 points when x is 4 and when x is -1. Do we need to find the y coordinates? No. It would be good enough just to know the x coordinates. Because then we can set up our integral, and we notice that the blue one's on top, so it's the x plus 1 minus, and we can simplify that. The nice thing about areas between curves is usually they're really simple integrals to do. Right? Wouldn't you like your test to have only these integrals tomorrow? And this time I'm not going to make you write down the work. I'm not even going to show you the work. I'm just going to say, trust me, it's 125 over 6. Because you'll never double check that. Well, maybe some of you will. I know some of you are out to get me. I know. You're like, it's probably making mental math mistakes everywhere. I'm going to go home and double check these numbers. So sometimes they won't give you the graphs. So you would have to draw a picture on your own. Y equals e to the x. Y equals the square root of x. And you want to find the area between the two graphs. You sort of imagine in your head, you're like, okay, I know this point is 1 comma e. I know this point is 1 comma 1. So I know my square root graph has to be below my e to the x graph. And we want to find that area, which is a really weird looking area. So we set it up as an integral between 0 and 1. There's no intersection points because they told us between the lines 0 and 1. So we just have to do the green graph minus the area under the blue graph, and we'll get that nice shade of blue in between. Again, I'd probably change my square root of x to the half so I can really do easy. Add 1 to the exponent and divide. You could separate it, but you wouldn't need to. You could do that all together in one as well. And plugging these things in, we get e minus 1 here, 2/3 there, as you get higher level, like they could make this a multiple choice question, and they have e minus 5/3 as an answer, and you're like, oh, I have to do the work to find out if this is right. You can't just look at an answer and say, this feels right. So why don't you try the next one on your own? It's not too bad. don't have crayons. I was looking if I actually had crayons that you could borrow to color it in, but maybe you want to use a highlighter. But try this next one on your own. I'd like to check how you did. Oops.